Hello everybody and welcome back. I have to start this video with an apology. An apology to the people who made the CW-5000 and sold it to me. Because somebody suggested that I might have been scammed just because it was so cheap, and I jumped on that bandwagon and I've been riding it for too long. And also, they didn't. The machine has a fault, but I'll explain what that fault is, and it is not a design fault. Now, let's go over the compressor in itself, the way it works, because I spent nearly 2 nights completely reverse engineering this thing and figuring out what is wrong, and now that I know what's happening, it's not so bad. So let's start out with the thing that we want to cool, water. In the CW-5000, water is in a big tub, and also in there is a heat exchanger, which is a coil, and that sits in the water, and the water is the medium that we want to cool down. This coil, in terms of an AC, is called the evaporator. I'm going to call it E. Also, we have a big compressor, which I'm going to call K. And this compressor is basically a pump that pumps gas and also makes sure that the gas that is coming out of it has higher pressure than the gas going into it. And these things are sealed, they're self-lubricating, whatever. We have another thing in the back of here, which is a heat exchanger, and that one has 2 big fans, and those fans will push air through it at great speed to remove as much heat as they can from the heat exchanger. And in terms of an AC, this is called the condenser. So the compressor compresses our refrigerant, which turns into a gaseous form and sends it into the condenser, where it gets cooled down and it becomes liquid again. From there on, it is pumped right into the evaporator. There are some capillary lines here, there may be a small reservoir down here, but that's not the important part here. And once it gets back out of the evaporator, the gas has evaporated. It has taken in a lot of energy to do so, and we have very, very cold temperatures in the evaporator, and this turns our water cold. So the condenser gets warm, the evaporator gets cold. And after we're done with that, the whole thing starts all over again. The refrigerant returns to the compressor compresses it, and so on and so forth. Now, this setup inside the CW-5000 has something extra, and that something is called a bypass valve. And the bypass valve goes from the hot side, the pressure side of the compressor, right to the start of the evaporator, so right here. And there is a mechanical switch that can be operated by a magnetic solenoid, and this will turn this on or off. So in normal state, when it's operating, this valve is closed and we have a real AC. In a second state, this valve here is opened and hot gas from the compressor can get straight into the evaporator. This happens, or when this happens, the whole system goes into a sort of stalemate. It doesn't really cool anymore, or it loses a lot of its cooling power, because sure, you still have some gas going this way, and you have some of it going through the condenser, turning into liquid and evaporating in the evaporator. But this is like turning this valve on and off is like turning the compressor on and off. Now, why is this so important? Because in the cooling cycle of the CW-5000, this bypass valve has a very great role, and I'll get to that now. Now, suppose we have the temperature on an axis, on our y-axis, and we've got time on our x-axis. So this here is temp, and this here, that's stupid, this here is time. And we have several set points. For example, there is a temperature that we can set. For example, we want to set 16 degrees as the temperature where we want our cooling to turn on. There is something called the hysteresis, which is a second value that gets added to that 16, which is slightly above that. This here is our set temp, which is 16, and our hysteresis is 16.8. Now, fine. Usually, now we start out and we've got a temperature, I don't know, we're starting out at 10 degrees. Over time, our temperature is going to rise. It is going to go past the 16, and it's going to hit the 16.8, which is the set temperature plus the hysteresis. At that point, our cooling system turns on, and it turns on full power, and it's going to start dragging this temperature down, and that is going to go pretty quickly up to the point where it hits the set temperature. Now, in a normal AC, you would say, okay, now is the time to turn it back off again. And then it would heat back up again, and you would turn it back off. This leads to something that is called a massive on-off situation for an AC, because starting the AC and stopping it is basically the thing that has the most wear. So what happens at this point, right here, is that the bypass valve opens. And as it opens, the whole AC part of the water chiller becomes a lot less effective. So it keeps on cooling, but just a little. And over time it will cool a little, but not very much. Now there's a second set point, which is set inside the machine, and that is our set temp -2, and that is 14 degrees in this case. And if we put this in here, which is our set -2, and this is hard configured in the controller, the temperature will go down here, and it will just stop. At that point, right here, the whole chiller AC is going to turn off. Because it doesn't want to cool further down than 2 degrees less than what you set, because it has to be within some type of very strict consignment of temperatures. You don't want it to get too cold. Now, all the time from on to off, this AC 5000, the CW-5000 consumes about 500 watts of power. A little less when the bypass is open, but that is then like 495 or something. There's very little change. Now, you might think, oh, that's bad. And I thought that's bad. I was under the impression that this thing wasn't working right. But the reason why it does that is a completely different one. Now, suppose you put a load on this system and you're actually taking cold water out of it and returning warm water. What happens is that you get very fast heating up to the point where you get another on event and it turns on. You get good cooling to the point where it opens the bypass valve. And then the cooling just drops. So it will do just a little dip under that and come back up again, where it will close the bypass valve. And it will start cooling again as soon as it gets down here. So you have it fluctuating around the set temperature very closely. And it does that by just opening and closing the bypass valve. And that is the thing that makes this chiller so effective, because it stays within a very small temperature variant by just modulating its cooling, not by turning the whole compressor on and off, but by opening and closing the bypass valve. This is to a part inefficient, because every time that the bypass valve is open, the operation of the compressor and the whole cooling system is inefficient. But you get your full efficiency back as soon as you go back up over this set temperature. So that is the reason why the setup is the way it is. Now, what's wrong with my compressor? My compressor apparently has a fault in the valve. When my valve, or when the valve on my compressor opens, it actually releases too much pressure, so it actually stops cooling. And that has 2 reasons. The first reason is the valve isn't okay. It's making a ton of noise and the cooling just breaks down completely. But where I have my compressor, it's only about 3 to 4 degrees above the set temperature. So my compressor never gathers enough momentum to really push past the set temperature line and get towards the set temperature -2. So there's something wrong with my compressor, but it is not a design flaw, as I stated in the last video. The design is really good, and it has something to do with the duty cycle and the running time of ACs. And the way this is built, this is basically meant to last a long time, to have a long life, but to achieve that, they're willing to actually burn a little bit more energy than they would really need. And that's the whole thing about it. It is really simple when you think about it. The only thing that kind of irked me was that I asked so many people for information about this, how this works, and how these things are done and how this is made, and nobody actually gave me any information. I had to find all of this out myself. I do have to give a very, very, very big thank you to a very lovely lady named Sue, and she works in China, and she's a friend of mine, and she actually did a lot of phone calls in China for me, finding out more about the CW-5000 and actually getting in touch with people who were able to really lend help. So, Sue, thank you very much. Now, on the interesting thing of this, I still think that some of the controlling of the built-in controller of the CW-5000 is kind of strange. So I ordered parts so I can build my own thermostat with an Arduino, and that basically does exactly the same, just maybe a little bit smarter, so that it can actually detect when there's load and that it doesn't have to go all the way to 2 degrees under the set temperature, things like that. And it will be really interesting to get that working. And for a start, if I can't get my machine replaced because my valve definitely isn't really working, I have a workaround, which is just adding a second switch to the CW-5000 to eliminate this valve. So it will just be working between the hysteresis temperature and the set temperature -2 degrees. That is a bit more variance that I would like to have, but I tried it and it works pretty well, and it works pretty well with my laser because my laser doesn't have that much of a load, and since it is so cold down here anyway, I think I can get away with it. So that already was everything that I wanted to say. So really, I am sorry for saying somebody tricked me, because I wasn't tricked. I just didn't understand it. And now that I do, I feel a lot smarter, but I really need to apologize. So thank you very much for watching, and bye-bye.